Today I'm going to talk about Minder, our faulty machine detection method for large-scale distributed model training. Minder is a joint work together with Tsinghua University, ByteDance, Northeastern University, and Harvard University. In distributed large language model training, faults have become increasingly common due to the enlarged training scale and extended durations involved. At ByteDance, the frequency of training faults has shown a strong correlation with task scale. For instance, in 2024, tasks utilizing over 1,000 machines experience an average of 2 faults per day. Quickly debugging when those faults occur is important to maintain high training efficiency, but unfortunately, such process is hard. Here we show an example of PCIe downgrading and justify how such process is tricky. When the PCIe downgrading issue occurs at a receiver NIC, it causes the NIC to reduce its data transmission rate to the GPU. As a result, the NIC buffer quickly filled up, triggering the NIC to send more PFC signals to the transmitter side. Before the transmitter could adjust and slow down its transmission, the switch buffer became overwhelmed by in-flight packets, leading to an increase in ECN signals. Consequently, the CNP at the faulty NIC surged as well. This chain reaction leads to a drop in the NIC throughput, reduce the GPU utilization, and thus affecting the overall training performance. In this scenario, actually the root cause was the downgraded PCIe in a single NIC, but the issue propagated rapidly to other machines, causing multiple abnormal metrics to emerge. When system developers and operators try to debug the problem, it could be confusing to figure out which one is the real root cause. Such unexpected anomalies are challenging to detect and often require significant time for diagnosis, leading to increased labor and resource costs. According to our analysis, over a 7-month production data in ByteDance, the average detection time to identify the faulty machine exceeds half an hour. Such delays can significantly escalate both costs and time. A straightforward approach is to start from inspecting the existing hardware and software logs from the machines. Engineers often rely on mining tools and offline benchmarking tests. However, such process is not efficient because the task continues running for some time before the issue is triggered. Additionally, the logs can usually be incomplete or contain redundant information. For instance, back in the PCIe downgrading case, the critical factor, which is PFC packet rates, was not explicitly included in our logs. Instead, the logs were cluttered with redundant data such as environmental parameters and warnings, which complicates the analysis. Moreover, the diagnosis process is time-consuming and labor-intensive. This highlights the urgent need for automatic and precise faulty machine detection. To address this, we first concluded an in-depth analysis of fault occurrence over 7 months data in 2023 and 2024 from the production environment at ByteDance. This table summarizes the type of faults, their frequencies, and the proportion of each type that a metric could indicate. Our analysis revealed that hardware faults constitute the majority of issues. Additionally, each metric estimates varying probabilities to signal different types of faults. Through our analysis, we identified several challenges in designing an accurate faulty machine detection system. First, faults can occur across a wide range of areas, from intra-host computation to inter-host networks, and from hardware to software communication libraries. These faults are diverse in both type and proportion. When examining faults and their corresponding metrics, we observe that the same fault can typically manifest as different anomalies in metrics. For instance, an ECC error might result in both high GPU and CPU utilization. Similarly, PCIe issues could lead to high GPU utilization or decreased NIC throughput. On the other way, the same metric anomaly does not always point to the same fault. For example, high GPU utilization could be associated with GPU hardware errors, GPU software errors, or even network issues. Besides, defining whether a behavior is an anomaly are actually task-dependent. For example, a GPU temperature of 7 degrees Celsius is considered abnormal when the GPU clock frequency is 1350 MHz, but it is a normal number for tasks where GPUs operate at a higher clock frequency of, for example, 1800 megahertz. The same principle would apply to other things like PFC rates. Additionally, we observe that metric data often contains noises because of the factors such as network jitters, inaccurate sensors, temperature fluctuations, timestamp misalignment, and more. These inconsistencies can mislead the detection process, making it less reliable. In response to these challenges, let's conclude some insights. We first find that metrics across machines exhibit consistent behavior during parallel distributed training at per second observation level. When a fault occurs, such as PCIe downgrading again, the PFC rate demonstrates distinctive differences compared to normal operation. This principle can be extended to other metrics, offering a potential pathway for systematically identifying those faults. To denoise the time series data, we can leverage the notion of abnormal continuity. Once a fault occurs, abnormal performance typically persists across several consecutive windows per second. This can be used as a reliable indicator for identifying faulty machines and ruling out noises. To address task-dependent anomalies, we find that we can actually use individual models to represent each monitoring metric. Since the monitoring metrics are independent themselves, these models and their respective metric data are utilized independently for both denoising and detection purposes. To summarize, we incorporate multiple metrics from comprehensive monitoring and train individual models to address the complex correlations between fault types and metrics. These models are then applied for denoising, effectively filtering out jitters and noises in the data. With those insights, we built Minder, a fault detection system for large language model training. Minder processes metric data from each time window and generates an alert when a faulty machine is detected. The design consists of two key components: constructing a VAE-based parametric models for anomaly detection and a similarity and continuity-based check to ensure accurate fault identification. To construct a parametric model, because labeling task-dependent faults is actually challenging and may not be practical, we choose to use unsupervised learning here. VAE is widely used for denoising and compressing high-dimensional features with its strong reconstruction capabilities, and it's proved to be an efficient solution in Minder. Various statistical and machine learning techniques can be incorporated into VAE's encoder and decoder to capture temporal characteristics. In Minder, we employ LSTM as both encoder and decoder, given our data consists of temporal time series. LSTM is also shown suitable in our case, as it considers both forward and backward information, enabling it to extract a complete correspondence information from the data. With the constructed parametric models, Minder achieves runtime detection that applies the concepts of machine-level similarity and continuity from our insights. For each time window, Minder first preprocesses the raw data and uses the pre-trained model for reconstruction. It then compares the similarity among all machines by analyzing the z-score of the same metric. In the presence of a faulty machine, its z-score is significantly higher than a predefined threshold. Minder then shifts the time window and identifies machines that consistently exhibit anomalies across consecutive windows as faulty, thereby filtering out false alarms. One important thing here is the metric prioritization. Minder calculates the maximum z-score of a metric across all machines and maintains a decision tree on metric selection. I'll bypass the decision tree part here in the talk, and please check our paper for more details. Minder has been successfully deployed in ByteDance for the machine learning training tasks, monitoring tasks at the scale of our assault machines. In our evaluation, Minder reduces detection time by 99% compared to previous manual diagnosis processes. We compared the Minder with a baseline of Mahalanobis distance-based alternate detection method, and they demonstrated Minder's performance by effectively detecting actual faults while maintaining a lower false alarm rate. This improvement is attributed to Minder's use of VAE for denosing and its ability to extract data patterns for more accurate distance calculations. We analyzed the breakdown of fault types and found that Minder achieves an overall precision of 90%, effectively handling CPU and GPU-related errors. From our detection results, we also discovered that models focusing on PFC, CPU, and GPU metrics in our case are sufficient to address the majority of faults. In our ablation experiments, we explored the impact of including more and fewer metrics in the models. Adding more metrics introduced mutual interference, while fewer metrics finally reduced the capacity for outlier detection. In another experiment, we observed that without incorporating the concept of continuity, occasional short-term jitters does lead to an increase in false alarms. Minder addresses these challenges by effectively filtering out discrete bugs, noise, and jitters, ensuring more reliable fault detection. We also evaluated how Minder's ability to handle multiple faults. In a parallel setting, a higher number of concurrent faulty machines affects more communication groups, accelerating negative propagation across the cluster. The granularity of the monitoring data determines how well this propagation can be observed. With coarse-grained monitoring, dissimilar patterns may be overlooked due to short duration of each iteration. In our production environment, cases of concurrent faulty machines are actually rare and typically occur due to atomic switch reboots or switch-related AOC errors. To test Minder's effectiveness, we manually injected the PCIe downgrades into two NICs in a full machine training setup. Normal NICs exhibit high throughput at the start of each reduced scatter step to transmit data to the next node, while NICs with downgraded PCIe links show consistently low throughput. Minder was able to easily detect these anomalies and locate root causes using fine-grained monitoring. Throughout the implementation and detection process, we have gained valuable insights to share. Large-scale model training requires the collaborative efforts of multiple teams, which Minder being used alongside some other monitoring tools, such as DCGM, EOD, switch state monitoring, and so on. Minder can be extended in terms of data granularity and the range of available metrics, enhancing its adaptability and detection capabilities. Minder has demonstrated improved performance in detecting concurrent faulty machines using millisecond-level monitoring data, and can also identify new faults not present in the dataset. In Minder's production execution time, we also observed that some labels in the dataset were inaccurate due to short-term jitters and fluctuations, which highlights the importance of robust anomaly detection mechanisms. In conclusion, we emphasize the critical importance of faulty machine detection in distributed training due to its severe impacts on production environments. To address this, we built Minder, leveraging the concept of machine-level similarity and continuity. Our evaluation highlights Minder's ability to significantly reduce detection time while demonstrating the effectiveness of its design choices, making it a robust solution for fault detection in large-scale distributed systems. By this, I want to thank you for listening, and I'm happy to take questions.